Welcome back, everyone. So next we have Francois Lanusse, who is a researcher at CNRS, even harder than IAIFI, and also a researcher at Polymathic at the Simons Foundation. I think it is maybe hard to summarize what Francois does. If I have to use keywords, maybe I would say probabilistic machine learning and differentiable. But I'm sure he's worked very broadly in astrophysics, which I'm sure will be reflected on today's talk. Thank you.
Thank you. All right, so what I want to tell you about today has nothing to do with what Carol just mentioned. We're not going to talk about physical models. We're not going to talk about automatic differentiation. Very happy to chat with you guys about this after the talk. But what I want to tell you about today is, from my point of view, a new way of deploying deep learning in our scientific domains, in particular here astrophysics, based on this notion of foundation models that you probably already all have heard about. One disclaimer, we're not going to talk about LLMs. We're going to talk about database foundation models. All right, so the starting point for my talk is this plot, which shows you the number of papers in astrophysics on the archive that have used deep learning, CNNs, and neural networks over the past few years or so. You can clearly see the explosion that happened when we started to have deep neural networks around here. My first paper was maybe here at this point when it was still hipster to do deep learning. And you've seen this explosion of papers, and why people have really adopted these methods is because they're really powerful to make sense of ever more complicated data. But one thing that you do not necessarily see here is that the vast majority of all of these papers are using supervised learning for training the neural networks, and then those networks are trained from scratch all the time, so you don't reuse networks from work to work. And that I will say that this presents a fundamental limitation for how easy it is to use deep learning in our fields of science. So the first point that I want to make that has to do with this limitation of supervised learning is that who says supervised also says I need to have access to training data and labels for my training data. And those labels can be intrinsically difficult to get in our field. So one example of this is the one that you see here on the top right. Those are really rare examples of what are called strong gravitational lenses on the sky. If you can find them, you can do a lot of very interesting science to probe essentially the universe, but those are extremely rare. And so if I only have a few thousands of known of these objects, I cannot train a very large scale deep neural network to find them. The second situation is something that we do a lot now in astrophysics. We use simulation-based inference to go from data to inferring physical parameters. And that simulation-based inference usually relies on training a network to go from the data itself to some feature space and then doing the parameter inference. The issue is that in almost everything that's done today, those feature networks here are trained from scratch by anyone who wants to do simulation-based inference, which means that you need to run a lot of simulation just to train this feature extractor, and that becomes really costly. The second point is related to what I already said, the fact that those networks that are being trained right now on like current generation of applications are usually trained very specifically and so are almost never reused for anything else afterwards. And so that I would say that it limits, in practice, the ease at which you or your PhD students can come to some new data and derive some physical insights or physical results. All right. So that's the way we've been doing things. But meanwhile, in the more general computer science domain, we have seen this explosion of this new paradigm that's called essentially foundation models. So for those who are not really familiar with them, or even those that are familiar and will argue with me on the definition of what a foundation model is, I will say there are two important features. The first one is that I'm going to use a large amount of data to pre-train my foundation model, so a large model that is not necessarily trained for solving one specific task, but it's trained to build a good representation of what the data is. So how do you do this? You know about how to do this with ChatGPT, which is essentially next token prediction, but you can do this on any type of data with, for instance, this type of approach, where I'm training this encoder here to build a really good representation of what images are, just by asking it to predict what are the missing patches in this image. So this is not a task that really is meant to do anything in particular, but in order to solve it, this network needs to build a really good representation of the data. And the point is that once you have a network that has built that good representation, you can very easily adapt it to whatever task that you're interested in. So this is the next adaptation phase that you see here. So that paradigm has been really efficient for a number of things, in particular image classification. This is an example here from a paper that shows the classification accuracy that you can reach with image classification models. On the left, you have classical deep learning. So those are based on supervised fine-tuning, or supervised training, I should say. And you can see that with time, we get better and better architectures. We can get larger and larger models, and they get better accuracy, but they start to saturate because you cannot build a really large model on limited amount of supervised training data. And the example that you see on the right are taking a different approach. They first pre-train their model on a large amount of data without any sort of labels, and then they adapt their model for the classification task at hand. And by using this strategy, they can reach better performance. All right. So why am I interested in this? It's because this can really change, if we can adapt this paradigm to our use cases, the way that we do machine learning on astronomical data. The first point is that if we're successful at this, I will never have to retrain my own neural network from scratch. I will be able to reuse a model that is built by someone, that is available on the library, and then I can easily adapt it no matter what is the task that I want to solve. The second point is that if we can also deploy this paradigm, now we can do extremely powerful deep learning even in the regimes that were fundamentally limited by the low regime data. So for instance, if I want to find really rare or interesting object in a large mission like Euclid or LSST, now I will be able to do this with just a few examples of what I'm interested in. And then the final point, which has to do with this adaptation thing that I mentioned, is that if I can make it really easy for people to adapt my pre-trained model, then they can essentially do state-of-the-art machine learning by just deploying scikit-learn on top of a representation that my model would have produced. And so that allows you to do essentially almost as good as anyone could do without ever training any neural network, essentially. And so what we've been trying to do over the last year or so with my team at Polymathic has been to try to see if we can make this happen in practice. And so I'm going to tell you about the story about how we go from this idea of moving to this new paradigm to making it happen. And the first step has to do with collecting training data. And so here we are fundamentally meeting a challenge that is specific to our scientific field, is that gathering a very large amount of data for training such model is going to be pretty tricky. And the starting point for this is to look at essentially the amount of data that is used in the wild for those models that are trained on images or language. Here is an image and language dataset that has 2.3 billion of examples. We do not have any dataset that has of the similar size for machine learning training in our field, and there are very good reasons for that. The first point is that we're not going to just be concerned with getting just general images. We also need to understand the metadata with those images, for instance. So here is a patch of the sky that actually comes from Peter over here. It's the same patch of the sky, but seen by 3 different instruments. If I want to deploy machine learning on top of this, I cannot forget about where this image comes from. I need to also take into account the metadata for what was the instrument, what are the colors that are taken into this image, and what are the observing conditions that correspond to this image, if I want to be able to do inference robustly there. So capturing this metadata is not something that computer scientists really have to care as much about. Then we have this other issue that the type of data that we're looking at is very diverse. So these are conventional images, but in astronomy we also have spectra, we have time series, we have hyperspectral images. And so we have this additional difficulty here that the data is not as standard as text and images as in general computer science. All right. So our first project that I want to tell you about here is called the Multimodal Universe. We presented it at NeurIPS at the end of last year. And it's the first attempt at gathering a collection of large-scale data that will then allow you to train these foundation models. So how did we go about this? Well, so our first goal was to try to assemble a large amount of data that can come from many different sources, that can be of many different data types. So for instance, here images, but you can have time series, you can have hyperspectral images like here, into one consistent format. And the way that we did this is by following 3 different important pillars. The first one is to gather a community of people AI and astro experts. You have a picture of some of them here, because I may be an expert in this type of data, but I'm not an expert in those time series and such. And so the expertise for understanding and gathering all of these different data sets is really distributed among a number of experts. And so it's important to bring them together. The second important aspect is that once everybody is in the same room and can bring in their expertise about their own knowledge of the data, we need to find a way to standardize conventions for how we're going to store the data, what are the important metadata to store along with the data, and how the data can then be accessed in a way that is fast to train a large language, a large machine learning model. And finally, in addition to just accessing and gathering the data, there's also a lot of subtlety that goes with every little data set. What are the examples that I want to include? What are the examples that I want to exclude? And that requires a lot of expertise. And we want to demonstrate also application of this single data set to a lot of different fields in astrophysics afterwards. So we gathered this team, and we came up with this strategy to gather our multimodal data set here. So the idea is that we are going to come from a collection of surveys, essentially publicly available data, and we are going to ask the domain expert, the scientist, to write what we call download scripts. So those scripts are pretty simple, pretty easy to write by a domain expert, and they essentially are just interacting with the original archive, the original survey here, downloading all the data that is necessary, and then formatting that data in the standard pattern, standard format that we have agreed upon, such that then all of these different surveys can be concatenated in a standard form and downloaded in one location. And so that's what we did at the Flatiron Institute. And at that point, all the different data that can come from many different places, many different formats, will be stored in a unified Hugging Face format data set. And the additional thing that we provide is also the ability to do cross-matching across the different surveys. So for instance, if I'm interested in this galaxy here, it's also something that you heard from Alex just before. We will be interested in multimodal machine learning to find different types of observation, different types of modalities that relate to the same physical object. And so we make that possible through these sort of utilities. So at the end of the day, in the first version of this data set, we have a large collection of different data sources. So for instance, we have essentially all of SDSS, we had all of the DAISY available data, but a bunch of also optical images, time series, and what we call tabular data. They are conventional catalogs. The important things that we impose in this data collection is to be pretty minimal in the metadata that we want to collect, but those metadata will be very important to help your machine learning model understand what images we're looking at or what spectra we're looking at. So for an image, for instance, we don't only have the image, we also have like the variance maps. We have information about what bands, what instrument and what bands was used to acquire this image, information about the observing conditions and, let's say, the pixel scale. And with this small set of standardized metadata, we can pretty well describe all the data that we've acquired. And then the last piece in this format is that we also store data in a way that is then going to be very easy to search and cross-match on the sky by using a breakdown of the data into Hill-Peaks regions. I'm going to skip over the details, but at the end of the day, I encourage you to follow this link if you want to see the data itself. We have of the order of 150 million images, many time series, and many spectra when we also account for low-resolution spectra from Gaia. So all of this in one consistent format in one place. And then if you want to play with this, you can find also in the slide this notebook here, which will show you that in 3, 4, maybe 10 lines of code, okay, you can access this data set, you can get the data, and you can also see all this metadata that I told you about. So it's very easy to use. All right. So we've solved the first hurdle. We've gone from many data living in many different places to a standardized location. Now, what we want to do is to find good architecture choices and training strategies that will allow us to build foundation models at scale that can also understand all of this data in all of its complexity. So if I want to think about this as a spectrum of kind of models that we could build here, on the left, you have very specific models that would work really well for one particular type of data. And on the right, this is where we would like to be, to have one type of model that you can apply to all the data that you have, no matter what data type, no matter what data origin you have. So the left is what we've been doing for a long time. This is some work that I've done in the past to represent galaxy images. This is work that Peter has done to represent spectra. But every such work that we've done, we're always limited to one data modality. And if I want to think about the ultimate goal, to have one model that can work on all the data, this is an example of such a model. We're not exactly there yet, but this is an example of going into that direction where they build a transformer model that can do image classification directly from the raw bytes of your data file. So at this point, we actually don't care about what is the data modality. We work directly at the level of bytes. So we're not there yet, although we like to be. And I'm going to show you our progression on this scale from our first model that's called AstroClip to the next generation that we are about to release publicly. So the first thing is something that Alex already told you about, AstroClip, which is our first attempt at building a foundation model that can connect different modalities of data together. So this is based on this clip idea, which was made famous, let's say, by OpenAI a few years ago, where the idea is that I want to build those encoder models that go from, in this case, images and text, in a way that satisfies this loss function. And so what this loss function means is that if I have a text and an image that correspond to the same object, I want their embeddings, the vector embeddings that come out of those encoders, to be well aligned with each other. And if the pair is not associated, I want them to be misaligned. So this you can do, and once you've trained such model, one of the very nice features that you get is that they are really reusable. So they have been, in particular, the key to the first generation of vision image model, the one that we're able to generate images based on text. But here is an even simpler example. If I have a trained image encoder, I can turn it into a classifier for this image by just looking at which of those sentences will align the best with my text, with my image, if I replace the object by one word or another. So we exactly use this strategy for our model, but we replaced images and text by images and spectra. So here we have a spectrum encoder. It's a pretty large transformer model, and same thing for images. It's a different architecture, but also transformer-based. And we train it such that if I have two measurements that come from the same physical object, they should be well aligned in this latent space here. You have very nice features that come out of that training strategy. The first one is that you create a notion of similarity in that space. So what I'm showing you here on the left is if I take this, an image, I embed it into this space, and then I look for all the surrounding images in that latent space. Here are the ones that I will retrieve. And so they look similar to the eye, but what we'll show just after is that they're beyond being just similar to the eye, they're also very similar in terms of their physical properties, which is going to be very interesting for us. And one way that you can then exploit this kind of representation, for instance, to build a prediction model for some physical property, is just by doing something as simple as nearest neighbor prediction. So here, for instance, I take an image, I embed it into this space, and then I look for which spectrum is going to be the closest match to that image here. And these spectra here, which are training data essentially, they come with associated labels because we can analyze them from a physical point of view. And if I just find the closest one in this representation space, and I use that as a prediction for what is the physical property of this thing, I'm going to get a non-trivial estimator, which is actually reaching state-of-the-art performance. So this doesn't work, but I'm going to show you an example of what I mean on the most used example of physical property prediction that you can do on such images, where we're trying to predict the distance or the redshift of an image of a galaxy, given its image or just its color, its photometry. So what you see here on the right, this is the most classical way of predicting this property, the distance of an object, by just looking at the color of the object. And so what you can see is that there is some amount of scatter if I try to build a predictor on this. If I trained a supervised machine learning model to go from the image to doing this prediction, this time I have more information because it's not just the color, it's also something to do with the morphology, everything that's happening in the image. And so I can reduce the scatter. The problem is that in order to train this, I potentially need a lot of training data with known labels. And the plot that I want to look at is going to be the one here on the left, which is taking this pre-built representation that come out of AstroClip model, and then build a prediction for redshift by just doing k-nearest neighbor regression. So exactly the same thing that I showed you before with zero shot. It's the very simple and trivial way of building a predictor. But what you can see is that the prediction quality that you get here is actually better than the supervised model and significantly better than the color alone model. So the main point here is that here, I've been able to build a prediction model for something that the model was never trained specifically for by very easy adaptation of that representation that was learned by the model. And so we can talk after the talk if you're interested in some of the interpretation for why we are able to extract physical information out of these things. But in the interest of time, I will skip a little bit of that. All right, so that was our first attempt. It's not perfect. It doesn't cover all the types of data that you want. And as we talked about in previous talks, there are some concern as to whether we capture all the information between modalities when we do this. But the next type of model that I want to tell you is bringing us closer to this idea of having one general model I can apply on all of my data. And we call this AON for Astronomical Omnimodal Network. So this is some work we've been doing over the last year with a pretty large team at Polymathic. In particular, co-led with Jeff Chen and Liam Parker. And so what this is going to try to do is to get all the data that we have gathered in this multimodal universe and train a single large transformer on this that then we can use for downstream application. So the first most important question when you start such a project is what will make Francois happy? And Francois is pretty difficult as a guy, difficult to make him happy. So the first thing is that I would be happy if I can build one model that can apply on any type of data. Why? Because then if I'm a user, I come to you with some new data that was acquired with a new telescope or something. I can directly use the pre-trained model. I don't need to work more to adapt it to my specific data. So that would be great. Then there's the next thing, and I would already be pretty happy with the first point. The next thing is that I would like to show that this large network that I'm going to train on all of this data is actually discovering something non-trivial about the data that I showed it that goes beyond what I've just specifically trained it for. And so that's what we're going to be trying to look for in what we're doing here. All right, so let me show you the type of data we threw at this model. What we try to do is to collect a diversity of data in terms of data modalities, in terms of data provenance, but also in terms of what kind of science you can do with this data. So the first element of this pile of data that we collected comes from the legacy surveys. So this is a pretty large imaging survey done with this very nice camera that you see here, and this is the type of images that it generates. And so we collected about 100 million of those images. Then we complemented this image data set by a different imaging survey that comes from, it's called HSC, which has different pixel size, different bands, so you're not exactly looking at the same wavelengths, different image quality, different depths. So they look similar in terms of images, but they actually change in terms of data quality and such. And then to go multimodal, we also collected spectra from the DAISY instrument that you see here. We collected almost all available spectra from SDSS, and we also collected spectra from the Gaia mission. The main point is that Gaia generates a lot of spectra. They're not as high resolution as the one that we can get here, but you have a lot more of them. The other thing to look at on this plot is that these kind of data sets are telling you about stars, for instance. That's what you can see here. And those ones are telling you more about galaxies. So you have an ensemble of data that covers different kind of science cases. So now the question is, we have all of this data, and it's pretty diverse. How do I build one machine learning model that can act on all of these different data types? So the strategies that we used here is very similar to what you do in current generation of language vision models, is to tokenize the different data sets into a standard, let's say, vocabulary, standard tokens. So the way that this works is essentially, for any data type, I can build an encoder-decoder system. And at the bottleneck of this encoder, I'm going to impose a discretization of the values that those codes here can take. So this is, let's say, the conventional way to do this. There are a bunch of different strategies to discretize those tokens, But at the end of the day, once you've done this, you can take an image, turn it into just numbers. They are just, let's say, indices of vectors in a dictionary. And you can decode those discrete numbers back into images if you so desire. The additional little difficulty that we need to handle in our case is that, as we said, we're not just interested in getting the images, but we also want to incorporate the metadata of these images as well, such that we can train with the information of the provenance of the data. So I won't go into all the details, but this plot here is showing some of the pieces of strategy that we use. In particular, at the input layers of this encoder model, we can also take into account the provenance and some information about the, let's say, the observing quality of these images by essentially tuning the first layer based on what is the provenance information that we provide to the model. So that gives us a way to incorporate the different sources of data. And at the end of the day, in this model, we capture about 39 different modalities that come from different instruments, different types of measurements and such. And so whether you have an image, a spectrum, a physical parameter, or something like a segmentation map, we can turn all of this into discrete tokens. So now that the data is nice and uniform, how do we train a model on it? So that's the point where we're going to go to a large-scale transformer. And what we're really going to be trying to incentivize is for the model to understand the connection between the different data sources. So the way that we do this is that we look for examples that are going to be seen, the same object, same galaxy, same star, between different data surveys, different data types. And that's where this ability in our multimodal universe to cross-match data sets is going to come very handy. So for instance, once I've taken an object like a galaxy and I found all of these instances of that particular object in the different data sets, I can tokenize all the data I have for that object into tokens, and then I train this large transformer-encoded model by randomly selecting a bunch of input tokens here and asking it to predict some remaining tokens. And so by doing this, in random combination of what comes in and what comes out, you essentially, at the end of the day, will build, by mass modeling, a model of all the joint and conditional distributions of whatever data modalities that you provide. So you can then model the probability of an image given a spectrum given an image, part of an image given part of a spectrum, etc. And then the final piece in this puzzle is training the entire thing. And so that is non-trivial. That requires a lot of compute. And we were very lucky to be part of what was called the Grand Challenge on the Jean Zay supercomputer, which you can barely see here on this image, that is installed next to Paris. And that was available to us through this Grand Challenge with about 1,400 GPUs. So when we trained, then we trained several generations of our models in several different sizes, going from a few 100 million parameters to 3 billion, even 10 billions. And what you can see here on those training curve is that as I go towards larger model, the training loss is going down. So that's nice. It's not necessarily what we care about, but it's nice to see that larger models make more sense of the data. All right, so what does it look like out of the box? So I'm not going to spend too much time on this because this is not the thing that we really care about for doing science, but it's pretty cool to see. So what I'm showing you here is sampling from the conditional distribution of those higher resolution images that HSC can generate or can provide, given a lower resolution image that this other survey can provide. And so when you see things flicker like that, the image that seems to be a little bit more zoomed in is the HSC image that has finer pixel scale, and the other image that's zoomed out is the input image. So this is an example of sampling conditionally on those things. The one that you see on the right is another example of this sort of super resolution, where what we provide to the model is this low resolution spectrum from this Gaia mission that you can see here as the red line. And the true spectrum here that we can measure from the ground would be this black line here. And what we ask from the model is to generate possible realization of the true spectrum given the low resolution one. And so what you can see, for instance, is that it's able to generate some of those features on the spectrum, even though they are not visible on the low resolution spectrum. So again, this is not really what we want to use for doing science, but it's just to show you that it's able to capture some of the complexity of the data. I'm going to skip this one in the interest of time. And I want to move on to the last point, to how do I use this large model for doing actual science at the end of the day. So to see how this becomes useful, we need to take a step back and think about how we were doing deep learning in the past, or like currently. So this is me about 10 years ago when I was doing some of my first projects on deep learning. And at the time, what I needed to do was to spend a lot of time building a large training set with very realistic simulations, very realistic data, spending a lot of time designing a complex network that could make sense of this data, worrying about pre-processing normalization issues, having my own GPU or GPUs and train for a long time, and then apply to the particular problem, which was here classifying this type of objects here that are stronger heterogeneous lenses. And when the paper was done, essentially all of that work was lost and thrown away. And what we can do now with this foundation model approach is that I only need to build a very small training set with realistic data to adapt my model. And then if I'm using good practices, I should be able to adapt it in a matter of minutes or seconds. That does not require having access to GPUs. And then I can finally do my science much, much faster. There are different ways that you can adapt your models. I'm already out of time, so I can't tell you about all of them. But I want to advertise this strategy, which is just the idea of taking an embedding out of the model that you've trained, and then very easy adaptation around that embedding. So the way that we do this on something like Aeon is that we essentially freeze this encoder, and then we have this model that can take any combination of data that you have. If you only have spectrum, you can take only spectrum. If you have images, you can take both of them. And you can get those as embeddings. And then you can adapt these embeddings to create a predictor for whatever you care about by just a simple linear layer or very simple attention layer. And so that is very easy. I won't have time to tell you about all these results, but we deployed it on a number of use cases. So this is a very simple example of classifying morphologies of galaxies. And this is as a function of the training set size, so the number of examples that you have to fine-tune or to adapt, let's say, the quality of your classification metric. And you can see that if I had a supervised model that I try to train with similar data set sizes, I would be much lower in terms of accuracy. The same thing works for different properties, such as predicting galaxy properties, even segmenting galaxy images, or one of the most interesting use cases, I think, finding similar examples in very large sets of data. So for instance, here, this is an example that I want to use as a query, and then I look for the embeddings that are most similar to that. And the 6 most similar example, and this one that I find in my data set that has 500,000 candidates, is a successful match to a strong gravitational lens. All right, so I'm gonna stop here, and just to tell you that the next steps of the thing that we're trying to do at Polymathic is to scale up these models to actually more data, and bringing those to the scientists in a way that is the most convenient to use, so that you can plug those in your analysis and no longer have to worry about, pesky aspects of data and training large language models, All right, thank you very much for listening.
Any questions for Francois?
Thanks for the nice talk, Francois. So my question is kind of related to the last few slides that you skipped. So in the old days of supervised training, you have to worry about this out-of-distribution problem when you train your model on one survey and apply it to another survey. So to what extent is using these large pre-trained models getting around this issue? And if so, my second follow-up question is, to what extent can we get away with pre-training the large models only on simulated data?
All right, so to answer your first question, you're exactly right. Those large foundation models are trained on some very obscure set of training data. You don't exactly know what went in. So that's why we're not using them directly as generative models without, taking care of this. We're using them as embedding models, where you can then adapt your embedding with such a thing, like training this adaptation matrix on your specific training set, where you essentially calibrate the response of the model for the particular problem that you care about. So because you do this calibration when you build your particular use case, it doesn't matter that much what went into the training of the original model, because you recalibrate for the use case you have with the training set. And then your second point was?
Second point is that
Yes, so simulations. So you could put some significant amount of simulated data in your training set, and that could help you discover the interesting relationship between your data. We chose not to do this because one of the things we really wanted to see is emergence just from data about what was going on in your data set. So I'll just show you one example of that here. This is an example of conditional generation of a spectrum given an image. But this particular combination of data was actually never included in the training set. So we never paired DESI images with DESI spectrum with HSC images. And it has learned by transitivity from the other example that we showed it, that for, if I put this as an image, this is probably the spectrum for this thing. So it's an example of emergent understanding of the connection between different data sets. And we wanted to see this directly from data without putting our own physical biases or potential biases in it.
Hi, Francois. Thank you for the talk. You might have partly answered my question, but I wanted to ask about Rubin and how Rubin, because the sort of leap in image quality is so great compared to these existing surveys, how Rubin fits into the embedding. But I think you might have answered it with this adaptation step. But I guess I'm now wondering, have you done anything with like Rubin DP1 or anything like that with this model?
Not yet. Ultimately what I think will happen is that every major data release of Rubin will be able to rebuild such a thing from scratch on all the new available Rubin data. But in the meantime, you can adapt the pre-trained model to the Rubin data by essentially just retraining just some of the input layers of the model to match the Rubin data. Yeah, that's one good strategy.
Thanks.
Hi, thank you for the talk. I'm interested in the first part of your presentation where you were talking about the collection of data. Mm-hmm. So from what I have understood, the expert helped you in labeling the data set?
So this is actually the most important time sink in building this sort of foundation models, is that in our type of fields, there is a lot of data available, but the data is very fragmented. It's hosted in a bunch of different repositories. And even if I knew how to access those repositories, if I have different types of data, they come with a lot of expertise on like what was the camera that was used, all of the systematics and such. So they did not help us build annotations. They helped us select the data that was relevant, which were the, when you go to like in a national numerical survey, you have thousands and thousands of quantities in the catalogs.
But the selection was based on the expertise knowledge, right?
So the selection of what is going to be relevant to keep is given by the experts, yes.
So did you provide a score for the importance given by the expert?
You could, yeah.
Because like in this is very similar to the medical field application where but they need to provide like a score for every expert because there could be a disagreement on what deems important by different experts.
So that's true. So what we did here was a little bit toyish in some sense because we gathered a very limited set of experts. And so we capture their own biases in this model. If we wanted to do it at a larger scale, we would need to have a better, sound approach like the one that you described. Okay. That's probably going to be useful in the next phase of this when we scale up.
Okay, thank you.
Hi, I had a question. You mentioned using k-nearest neighbors in the embedding space, which makes me wonder about the metric in the embedding space.
Yeah.
Do you just assume it's Euclidean? Or is there a reason to believe that's actually uniformly true and that distance in one point in the embedding space is really, it's an invariant, right? You could translate it in the embedding space or? So
that's a good question. There's no strong reason even to just embed in that space. We could embed on other manifolds. The only point here, two things. So when we train such a clip model, we train with this notion of similarity under this cosine similarity law. So that's kind of it's essentially the quantity that we then want to use to measure similarity between objects. And that is kind of a side effect of the training. But when we look at those large transformer models, we never incentivize specifically any sort of cosine similarity. It just happens as a side effect of using attention to build representation and to access representation. So to answer your question, I don't know exactly what is the right metric to use. This is pretty effective, but it is still a pretty open question for research of what is the right strategy for then discovering proximity in that space.
Yeah, I mean, I guess it becomes interesting in the case where, I mean, if every example has a lot of very similar neighbors, then it probably doesn't matter. But you know, if you have an example and all of a sudden you're really curious, like, are any of these neighbors actually similar or not? It'd be interesting to be able to answer that in some kind of with a metric.
The next phases of this that people do in practice for image searches, for instance, is to also have to be proactive in the way that you select example for training, to have very hard examples, to help structure the space in a way that you don't put everything at once and you separate better the thing that you really want to disentangle well and such. We didn't go to that level of complexity.
So apologies if I missed this, but it looks like your database has images and perhaps time series data that are of variable dimensions, variable size.
Yep.
And I was wondering if that's taken care of in the tokenization stage or elsewhere in the model.
That's a very good question. So within one of those data sets, they come from like one data source. They are all conforming to the same size, essentially. So except for time series, which can be variable, but like images, we kind of impose the image size. Then it's at the level of the machine learning model that we can adapt to different sizes. And so in this first generation of models, we are pretty dumb. So we kind of like either truncated or like extended things so that they match the same shape. But the next generation that we're currently doing is flexible to different sizes, and that's no longer as much of a concern.
Hey, Francois. Always fascinating to look what you're doing. The multimodal alignment. If you're using multiple modalities that are relatively similar to each other, such as, say, imaging data sets from SDSS and from HSC, which show often the same galaxies at some different resolutions, and then look at what the transformer does in order to kind of create a sort of a joint embedding and produce the other tokens. Do you find it is easier to do that if you have a lot of similarity between the tokens that are being embedded, or whether they are really different from each other and so something very different is being learned?
That's a great question. The answer is that I don't know. We haven't done this sort of experiments. Yeah. If you want to play with it and tell me the answer afterwards, they're welcome to.
So my question was, when you combine all of these modalities into your model, did you use a self-attention on each different modality and then concatenate them during runtime, or did you use something like cross-modal attention where you try and keep that cross-sectionality between modalities?
All right, so let me just pull up the plot again. Yeah, so here, essentially, there is no, this is just self-attention that happens inside this encoder. The way that you encode which modality you're looking at is by having a modality embedding. It's the same thing as positional embedding, but it's another vector that we add at the input. And that's the only place where we provide the information for where this token comes from. Then everything is done with self-attention, and then there is cross-attention from these embeddings that come out here to the decoder. To answer your question, yeah, there is no specific architecture like that. The reason for that is because then it's really scalable if this works.
Any last question? Great. Well, whoever goes first.
I had a quick question actually. Like, so in language models, like people have looked at these embedding vectors and then maybe use like sparse encoders to look at like if there's some dictionary. Have you tried that? Because you also have a very interesting embedding space.
Short answer is that we have an intern right now trying to look into this, but I don't know if this is going to be so interesting to look at. I don't have any results, but also I don't know if it's going to work really well in the same way that you can identify, semantics with language. So yeah, I don't know.
So let's thank Francois again.